Okay, greetings everyone. Welcome into my channel. I am Professor L, and this is a live stream for math help, math tutoring. So if you have math questions that you would like to see worked, post in the chat, and I'll give it a try. In the meantime, I'll be working on my board. I picked a topic that is back in Trig land, and it involves applications. So I'm going to go ahead and start erasing and just get into it. A happy Thursday. I hope everyone's doing well. Yeah, good evening for some math. And so I finally made it back to Trig land, which I'm happy about. And this application problem that I'm going to work tonight is involving right triangles, that they're not exactly special, but you can still use those trig functions for triangles that are not special. You just have to either look them up in a table, or you would plug them into your calculator and evaluate. So hopefully I'm successful with this application's problem involving an octagon. So I'll just say the octagon. All right. So, and I'm not going to take, I don't have a large compass, but I do have a yardstick. So I'm not going to be able to construct an octagon perfectly like the internet. But I did write one. I mean, I did watch a couple of videos on how they were constructing them, and I think that I can do a decent job just using the Cartesian coordinate system. So let me see. The octagon. So if you picture two sets of perpendicular lines that are overlaid exactly on top of each other, splitting them. And I want to get an exact measurement here. So let's say, how big do we want it? And I didn't get a chance to practice this on the board. So live, raw, uncut footage here. And I don't know if that's exactly straight, but we'll say, we'll do 20. Intuitively, I don't know. Okay, well, I know 6 is divided by 24, so. Or yeah, 6 divides 24, so we'll just go with that. And then half of 24 is 12. So if I put it right there in the middle, I should be able to do 12 in this direction, and then 12 this direction. Oops, I knew that was going to happen. Okay, I gotta hold it right in the middle. See how accurate this is. And I'm hoping, the worst case scenario, I'm gonna have to just redraw it, and it's really a pain if I have to do that. But if I line this up perfectly, 12, how could I figure out if that's exactly? Well, I could graph the identity function line, but still, it's still not going to give it to me. I have a protractor, but I don't. I just want to kind of eyeball it, you know? No, I mean, okay. So let's go ahead and just wait. I gotta get that right on 12. Right on 12. And while I'm doing this, I know it's kind of hard to kind of concentrate on something like this and talk, but that's what I'm tasked with here when I'm presenting. So what is getting an accurate sketch is so important. Okay. And hopefully I'm careful and I do this good, but if not, then I'll have to do it again. So let's see. And get it exact. So what we have an octagon is 8 sides. And in this problem, the only known value is the radius of one of these sides here. These vertices. So that's exactly okay. I can't lift it yet. And so what it's asking us to find is one of the sides given the radius known. And I got this question from an old trig book. All right, so we have it. Now all we have to do is just connect these sides. So let's see the best way to do that. I might be able to just rough sketch this, but might as well try and see if I can get it pretty accurate. We got this octagon, and I believe the radius is 36.8 if I remember the problem right, but I'll double check. And what it's asking is what is the side length, and then what is the radius of an actual circle that this octagon would be inscribed in. So if you were to draw a circle around this octagon, what would the radius be of the circle? Or I guess the circle is in, there's a circle. And I'm not gonna try to draw the circle, but I'll draw a segment of it. I like this problem and I picked it out specifically because it reminds me of the Archimedes pi problem. And what Archimedes did was he took a polygon of n number of sides and he kept making the sides of the polygon, he kept increasing the side number, the number of sides until he got a very close approximation for pi. So pi started, the oldest, the Babylonian square that had a diagonal of radical 2. And the Babylonians had an approximation for pi. It was 22 divided by 7, which is exactly 3.14. But before we had computers and we had calculators, we could estimate the values of pi and approximate pi out to an extremely large amount of digits in approximation, because pi is irrational and the digits don't repeat. Archimedes, one of his major works in math history was that he came up with a polygon, and he sides, and he used trigonometry to better approximate pi. And so thank you, Archimedes, for that. But we had to solve this whole pi problem in college. My class did, and I don't remember it, but this reminds me of it. And like, I remember it, and I have it worked out, and I saved my portfolio, but I can't remember. Like, I'm gonna have to go back and rework this problem because it was really cool. It was hard, and it wasn't one. It was one that was given to me at the beginning of the semester, and I really didn't appreciate it and actually solve it until like midterms. So it was a difficult one for me, anyway. I'm sure there's a lot of people that are way smarter than I am that would probably argue with me. But anyway, you can look it up. It's the Archimedes pi problem. It's very interesting. It would have been good for Pi Day or something like that. Maybe next year. Anyway, so I have my octagon, and what this problem is giving me is it's giving me one of these lengths here. It's saying that this is 30, I think it was 36. Hang on, let me double check. Okay, I have 36.8 worked out. 36.8. And it's asking for x. It's asking for that distance there. That's a really thin line, so I don't want to mess it up too bad. But so this is kind of how, and I didn't get to work this out on the board, but I did do a little bit of work on this problem. And so what I did was I used the fact that this right here is a 90-degree angle. And I don't need my yardstick again. And what I did was I took and I made a kite out of one of these. And I don't know if this is like the official popular way to solve it. This is how I figured it out. And I had to watch a couple of videos to relearn the characteristics of a kite, and a kite has some characteristics about it and some symmetry. So it turns out that I don't necessarily need all the values for the kite, because I can just what I did was I split this one up. I think this was the main value from the kite that I used, is the fact that all four of these angles here are right angles. And so what it's asking is for, hang on a second. So for the radius of the circle, okay. So the radius of the circle is going to be, so here's, all right, so we know this is 36. This is 36. And this is where, so we have a circle in here somehow. So if you can imagine, it's within the bounds of this kite. And so there's one that's outside, but there's also one that's inside. And so the radius cannot be, of the circle cannot be larger than 36.8. It has to be smaller. So I'm going to go ahead and write this up here, directions. Okay. And I ruined this marker. Hang on. Dried it out. There we go. Okay. So all it's saying is to find the inscribed, hang on, inscribed circle radius. Hold on. Find the radius of the circle inscribed. All right, bear with me. Find the radius in okay, so it said find the radius of the circle and find side length. Okay, we'll just say length of one side. All right. So we're looking for the circle, the radius of the circle. And we're looking for this value right here, x. So what I did was let me see how I started this thing. All right, so I'm going to first start by taking this triangle here and I know the two sides, so 36.8 and 36.8. So I have this triangle here. So I have, which is it's basically, it's a right triangle with two congruent sides. Then that means that it's a right isosceles. Let's see if I can make this exactly right. Get a little bit closer. It's been a while since I've drew a triangle. We're just going to put it here. Hang on. I think I can do it again. All right. Maybe I should cut the video and just cut out all these little bloopers or something, or I don't know, maybe get a laughing track. Okay, so we've got this thing going on. I'm just trying to draw this triangle. So this is 36.8 and 36.8. And so I can find this length here by using the Pythagorean. So this would be A, B, and C. And then by Pythagorean, I have a squared plus b squared equals c squared. So we'll just plug in a and b here. So we've got 36.8 squared plus 36.8 squared equaling c squared. And now I'll probably go ahead and just plug that in my calculator. So that's 36.8 squared. I'm getting 1,354.24 plus 1,354.24, and that equals c squared. So I'm getting 2708.48 equals c squared. So to solve for c, you have to take square root. So you got c equals and that's going to be 52 point. So we'll just do it, list all the digits it gives me. 52.0430591. All right. So that is this length here, this entire length here is 52.04. And really, I should go ahead and draw that in there because what this is this is a kite. The kite has a special property where they this line right here is actually a perpendicular bisector. So it cuts the triangle, or it cuts the kite into two equal parts, and it creates some congruent relationships between that symmetry. So I can basically, since a perpendicular line, perpendicular bisector bisects a line segment into two equal parts. That means that if this entire line segment is 52.04, then since I know that this is a perpendicular bisector, then I can go ahead and say divided by 2 is going to give me one of these side lengths. So one of these side lengths. So this side length here for this smaller triangle is 26.02. So let's see what I want to do, how I want to put this in here. I'm going to make another triangle here to represent one of these triangles. So I now have this thing. And I have this side length. We'll just say that this is A. So A is going to be 26.022152955. And that would be B and C on this triangle. So what I have done is drawn this triangle. So C in this case is 36.8. And then if we could just round all the values to 1/10, we'll say that that's just 26. Say 26. We'll just go ahead and say 0.02. Now I want to find this side length. So I'm going to again use Pythagorean. So a squared is 26.02 squared. X is going to be b. So plus x squared equals 36.8 squared. So we've got x squared equals 36.8 squared minus 26.02 squared. So we'll go ahead and take the square root of both sides. And then we're going to get, let's see, we'll figure out what that is. 30 square root of 36.8 squared minus 26.02 squared. Okay, I'm getting 26.02. 26.02. So we cut this isosceles triangle in half, and we got another isosceles triangle because 26.02 is what I got, which is exactly the same. That means that two congruent sides in a right triangle is going to give you a right isosceles again. So that's okay. But more importantly, I found this value, 2602. And so 2602. Wait a second, how is that going to help me? Okay, so this is 2602. Okay, I need this side length. I need to find x here. Okay, so I have this one. This is a 90-degree angle. Oh yeah, I know one more angle. Okay, so in an octagon, the inscribed angle, that angle right there. So I know that it's 360 divided by 8. So the interior angle is all 45 degrees, but this angle right here is 135. So for this little triangle, here, where do I put the little triangle? This one. I'll just put it in here somewhere. So I know that this is 2602, and that angle right there is going to be, it's a bisector, so you can divide that one by 2 as well. 135 divided by 2. So that's 67.5. So theta 67.5. So let's see what we can do. I think since we know, yeah, we can use, so we'll say opposite over hypotenuse. Yeah, I guess we can. I guess we can do that. I was just trying to think if there was a better way. Adjacent over opposite, we would find this side. Let's just see what happens. All right, so by definition, sine is opposite over hypotenuse, and I want to know hypotenuse, so that's the best thing to do is use the trig function involved. So by definition, you've got sine. All right, so we're going to say sine of theta, 67.5. We're going to say that equals 26 26.02. 26.02 over x, because it's opposite over hypotenuse. All right, and so then we've got this set up, so now we just have to solve for x. And you could set up a proportion and cross multiply that way. So that's going to give you x sine 67.5 equals 26.02. And then to solve for x, we're just going to divide off that sine 67.5. So we've got x approximately, because it's going to be an approximation. I'm going to plug it into my calculator. So although I remember the sine tables, I don't remember how to even use them. It's been so long. So I actually found one of my old trig books, and it has the sine tables in it. So I'm kind of halfway wanting to take some pictures of it and like post it on my page or something. It's cool. I don't want to get in trouble for copyright. So if it's education purposes, I guess I got a little wiggle room there. All right, so I'm just typing in 26.02 divided by the sine of 67.5 and making sure that your calculator is in degrees mode. And it's giving you 28.16. So it's approximately 28.16305. Okay. And then, why do we need to find that other side now? All right, so we have to find the radius now. And I looked up a formula for the inscribed radius because there is one, but I'm interested to see if I could figure out why it's this way. Okay. It says, and it's, you find the radius of the circle by finding the area of the octagon. So you use this formula. So area times, what is it? Hang on. No, sorry. It's 8. It's the number of sides. I think this is just polygon generalization formula. So it's radical 2 minus 1 times the radius squared. So you have to calculate the area of the hang on, it was 2. Hold on. This is for the inscribed radius. Hang on, I have to calculate the area. The area is actually 2s squared. 2s squared times 1 plus so. But since we found the side length, we can actually calculate the area. So it's going to be 2 times that side length. What was it? 28.2. So we'll say 2 times 28.2 squared times 1 plus radical 2. So 28 squared times 2 times 1 plus radical 2. All right, so I'm getting for the area. I'm filling my board up today, I guess. The area is going to be 3,829.9. Sorry, say a 9 and write a 2. 18864. I also think it's the hour I picked, but we'll just go with it. I'm not trying to be perfect. So, all right. So approximately, we'll round that to the 10th place, and we'll say that's 0.9. And then we're going to take that value right there, and we're going to plug in there to calculate that radius. Okay. All right, and we're going to get here, so we'll do that. It's going to be 8 times the square root of 2 minus 1. So that's going to be 3829.9. So the area equals this times r squared. So we're going to divide off the 8 times radical 2 minus 1 here. And then you're going to get r squared equals and that is telling me r squared is 1155.780258. We're going to take the square root of that, and that should tell us r. Now I did not realize that I was out of frame. 7, 8. It's just because I need to go this way, I guess, so you can see. 7, 8. Hold on, I lost my calculation. Okay, 0, 2, 5, 8. Okay, I'm getting 33.99 for radius. So I'm getting 33 point, hang on. Where are we gonna write it? Right here. R equals 33.99. So we're just gonna say that's 34. So we've got S, what was it, 28 point here. All right, good. 40 minutes, a little bit longer than I wanted. But I'm gonna probably be going into Trig for a while. I'm glad to be back. It's my favorite probably subject of math is the Trig, and it's the one that really resonates with me. So by all means not an expert, but I do enjoy the subject. So I'm very glad to make it back. I am happy with my drawing. The calculations are a little all over the board, so I'll work on that. But I'm going to go ahead and end the stream now. And so, yeah, if you're watching, I greatly appreciate it. And yeah, I will just continue to try to show up every day and present something relevant, hopefully. And yeah, we'll just call it good for today. And so I really appreciate everyone, and I've been trying to take in all of the criticism constructively, and also compliments. I appreciate those too. And yeah, having a good time over here. So if you want to come hang out with me and do math, you're more than welcome to do that. And yeah, I will be back tomorrow, same time, same place, and we'll do it again. Bye for now.